So I want to, I'll just do a very quick introduction to myself. My name's Mike Bartley. I work for a company called Tessolve, but I help to organise these events here today, along with Peter and Paul. So thank you very much for their help as well, and to our sponsors, Synopsys and Cadence, who I think are in the room. I've seen Michael. Yeah, and Synopsys as well. Thank you very much. You'll find out a bit about what the EDA companies do, but they're also big local employers as well. So there are quite a few employers here today. But I'm going to talk about digital verification and see if I can minimize that a little bit, because we don't want that in the way. Okay. So we're going to do a lot on mixed signal and analog, and I'm going to talk about digital. Hopefully, then Peter will take over and talk about more about mixed signal, where we combine both digital and analog. Okay, so I'm going to start right at the beginning, if I can get the talk about what is design verification. So this is in general before I move into what digital is. So given it as quite a formal definition, we're trying to gain confidence that our design meets the requirements or specification. Okay, it is very much a process. So it's a process we go through, and we're gaining confidence. Now that may sound quite strange to say that what we're trying to do is gain confidence rather than make sure there's zero bugs. But as you enter the industry and you see how complex the designs are, guaranteeing zero bugs is virtually impossible. So as verification engineers, what we tend to do is try to get as much confidence as we can. And we have lots of different metrics to allow us to do that. Okay, so and it's a process, so we're constantly trying to improve those metrics and gain more and more confidence. And at some point, you just have to say, I've done as much as I can, and that might be a market pressure. So, for example, if you're working on a mobile phone chip, if you're working for Apple, and it looks like you're going to miss the Christmas market, then you're probably going to lose half a year's income or revenue. So quite often it's time to market that determines when you sign off and when you say this chip is ready. Now the reason you have to be as confident as possible is because quite often the mask sets now. So when you go to fabrication, it's quite an expensive process. So if you're used to writing software, you can press a compile button, and if you find a bug, you can press the compile button again. Unfortunately, in silicon, rather than press a compile button, you've got about $5 to $10 million plus a 3-month wait. So it's a lot more expensive compile button when you're dealing with semiconductors. So we try and get as much confidence as we can, but are also aware of the market windows. So you're trying to balance that, okay, between confidence and time to market. And as I said, sometimes if you miss a market, and obviously for a mobile phone, Christmas is quite a major time, especially for someone like Apple or Samsung. Okay. Some other industries like automotive, the market window is probably less pressure and it's more about safety. And for something like automotive, again, you're trying to get as much confidence as you can, but you actually got quite a lot of sign-off criteria that you have to meet in order to be able to use that chip in the automotive industry, because there's a safety element involved. Now, we do a lot of different types of verification: functional, performance, timing, and physical. I'm going to talk about function, and that means does the chip function correctly? Performance might be that you meet a certain benchmark, for example. Okay. And I also want to distinguish between verification and validation. Again, this is terms that often come up in software, but quite often validation means getting the correct requirements and specification. You're trying to meet the customer's needs and demands, or the marketing department. So with a mobile phone, you haven't got a specific customer, you've got a market, but you've got a marketing department that will give you those requirements. And similarly for automotive, if you're trying to create an autonomous driving chip, then you may have a certain number of LiDAR on your car, and that you're trying to fuse together all the feeds from those LiDAR to try and make a decision whether somebody's in the way and you need to brake or not. Okay. But again, that will come through as a specification from your market department, or you may have a very specific customer in mind. And I know companies like ARM, although they do chips for the general market, they've usually got 2 or 3 lead customers who will say, this must be on the chip, this must be on the chip, and this must be on the chip. Okay. Okay, and whereas verification, once you've got those requirements and specifications, as I said, it's a process of getting confidence that you've met that. Okay, so you separate requirements and specification gathering, which is validation, from verification, which says, am I meeting those requirements? And you quite often say validation is, am I building the right thing? And verification is, am I building the thing right? And so if you that's one quick way of trying to remember it. Some companies do use validation when they mean verification, just to confuse the issues. You just be aware of that. Intel, for example. And sometimes validation, we mean, does the silicon, when it comes back, meet its spec? Okay, and there we're not just talking about function, we're talking a lot more about the physical realization. And so you're talking a lot more about electrical parameters, for example. Okay. A lot of people will talk to you about independence and verification. It is very important. And the reason is because in the process there, as you go from the specification, it's normally written in natural language, and typically as part of our industries happens to be English, which is useful on the international stage, because if you work with any foreign company, I remember turning up at STMicro, and all the French people had learned English as part of their degrees, so they could understand specifications, because it is the international language. So quite often those specifications are written in English, but they get interpreted. Okay, because they're written in English, you have to interpret them. Okay, and quite often there's a misinterpretation. So if the designer verifies their own code, there's a very strong chance that whatever they assumed about the specification and put into their design, they're just going to verify that their assumptions were correct. Okay, so what we say is that's a sort of single point of failure. An independent verification engineer will give a different interpretation, and to a large extent you're relying on the fact that they don't make the same misinterpretation unless the specification is really badly written, and everybody, oh, there's an error in the specification, but then that's not the fault of verification or designers. Okay, so that's why we have this independence. You get that separate interpretation, and actually verification engineers should be trained and to look at a specification and not accept any room for error or misinterpretation. If they look at a specification and say, oh, I'm not quite sure what that means, I'm going to assume it means this, then they're not very good verification engineer. You do have to go back and say, can you explain to me exactly what this line of the specification means? Okay, so that's why we have independence in verification, to avoid that single point of failure. It's very important. So if we try and put verification in context of the full IC design process, okay, and normally here you can see on the left-hand side, we're going from left to right here. You start with some sort of specification, which I've talked to you about. Concept, requirements is sometimes referred to as concept, okay, and we do an architectural specification and a more detailed design specification, which we then turn into an RTL model. We add in design for test for that, and that's for testing the silicon when it comes back. That's all about checking that the manufacturing process went ahead correctly, because quite often during manufacturing, as I said, it's a more sophisticated compile button in semiconductors. There will be errors in the fab. So a little bit of dust, for example, in the clean room can cause errors onto a silicon wafer, which will then mean that silicon wafer doesn't work or a particular chip on that doesn't work. Okay. But we are effectively verifying, so we're doing validation up to that RTL model, and then the functional verification kicks in. It maybe also starts with the design process, because the verification engineer may be looking at the design and making sure that the design is going to match the specification. But they really get involved in the RTL model. And they're verifying that RTL model. That's a digital model. RTL means register transfer level, which is a very digital model of the design. Okay, so I'm talking about digital verification here. Then goes into a synthesis flow, which effectively compiles it down to a gate level netlist. Okay, so when we go to the fab, first of all, you go to gates, and then you can convert those gates into transistors, and then the transistors will go into a layout, which will become a set of mask data, which you can fabricate. Okay, but a very, very long process. Some of the chips I've worked on take 4 or 5 years. This process depends on the sophistication of the chip you're designing, but most of them will take 2 to 3 years from concept to silicon. Okay, so that's the industry you're entering, and that's where functional verification sits. Okay, and I'm going to talk very much about functional verification. That's where we try to make sure that whatever's been implemented as a digital design meets that specification, and that's a more complicated bit, because you're going from a vague, hopefully not too vague, but an English specification to a digital design which has a very well-defined semantics. So you're going from something that hasn't got the semantics may be open to interpretation, to a digital design where the semantics aren't open to interpretation, a bit like a software language. Okay, and then from then on, you're comparing a digital model with a gate level model, and because they're both languages, you can actually just do equivalence checking, which is effectively a mathematical comparison of those two models to make sure that the function is equivalent. And then you do physical verification as well. But these are all machine readable. From RTL onwards, everything's machine readable, and therefore you can actually automate that. The only thing that's not machine readable is the specification written in natural language, although that is changing. Generative AI is meaning that we can actually start to interpret these specifications a lot better automatically into a digital, and then compare that with the RTL. Okay, and we do timing analysis. Okay, so if you ever looked at the processor in your laptop and it says it runs at 100 megahertz or 1 gigahertz. Okay, that's because we've got a clock in there that's running at a certain speed, and we need to make sure that the chip itself can run at that speed. And then we got performance. Other ones, I mentioned, but I'm not going to talk about performance. Safety, I hinted that for an automotive, you have to do safety verification, security, and power analysis. Power analysis, one of the reasons we've all got mobile phones and they last hopefully at least 24 hours is that the chips inside use a lot of low power techniques to go into sleep mode. That's why your screen keeps going off, because some chip inside is saying save power, go into sleep mode. And so you have to do that type of verification through power analysis as well. Security is very, very difficult, okay, because what you're trying to do is effectively trying to prove a negative, which is that secure data never ends up in an insecure place. Otherwise, somebody's potentially going to access secure data without the privileges to do that. So security verification is actually extremely difficult to do. But I'm not going to talk about that. I've only got my half an hour, and so I'm going to try and keep to mainly around functional verification. Okay, so these PPTs and the PDF of these PPTs will be available afterwards. Okay, so you can go through this in more detail if you want, but as I say, we won't be doing it now. Just to say on performance, quite often you're running benchmarks. Okay, and there's a number of benchmarks there. Okay, right. So why is verification so important? Okay, now there is an annual survey done by a chap called Harry Foster, who now works for a company called Siemens, was Mentor Graphics, got acquired by Siemens. Okay, and he looked at, and he does this survey every 2 years, so it's biannual. He does it every 2 years, and there's a lot of companies involved in this. I think there's probably around way over 2,000 people involved, which means it's statistically valid data. Okay, and they look at the amount of time that a project typically spends in verification. This is ASIC, this is not FPGA, by the way. They also do some numbers for FPGA. And typically, any project is between 50 and 60% of the time. And typically, an ASIC, particularly chip, will overall cost you, depending how complicated it is, anywhere between 10 million and 100 million, some more, to produce. So you're talking about between 5 million and 50 million to do your verification. So it's a very, very expensive process. I've worked on chips before for automotive. We were just recently working on a chip for autonomous driving chip. We had about 100 verification engineers on that chip because it was very complicated. Okay, and it has a major influence over three key project metrics. One is quality. Okay, because you're verifying function. Okay, and function is one of the main drivers in quality. Okay, if the chip doesn't do what you want, then it's not going to be very useful to anybody. If you have ever tried to use a piece of software that doesn't work, you'd know that it's effectively useless. Similar for chips, and to decrease costs as well. So if it's taking up 50-60% and I can do it more efficiently, if I can shave 10-20% off my verification effort, then I'm potentially saving the project anywhere between 1 million and 10 million. Okay. And the other one is timescales. Because it takes so long, it is potentially one of the you can a big impact on schedule. Quite often it's on the critical path. Verification is quite often on the critical path. So if you can again be more efficient in that, then you're hopefully hitting your time to or getting to market earlier, or beating the competition. Okay, we all work, the ASICs and semiconductor industry are very, very competitive, and so beating your competition to market is quite important as well. But it's complicated. What makes it complicated? Right, I'm going to give a very, very, very simple example and then quickly move on to something, show you how this explodes. Okay, so it's a 4-bit counter, okay, with 4 flip-flops, and all it's going to do is count up, and there's a reset as well. Okay, so if I've written this in Verilog rather than VHDL, but hopefully you can translate it to VHDL if you're a VHDL person. Okay, so you got a reset here, which is an asynchronous reset. Okay, because we're triggered on the postage of a clock or postage of reset. So it's an asynchronous reset. And that means it can go off any time. It doesn't have to wait for the clock edge to go off. If there's no reset, then it's just going to count up. So very, very simple. Every time there's a clock, I count up 1. Okay, and I can write a very, very simple test bench for that as well, because all I'm going to do is begin the process. I've got a definition of a clock there. So my clock is, depending on what the simulator timescale is, it's going to count up every 5. It's going to go to 1, and then it's going to flip and go to 0. So you've got a clock going up and down, up and down, up and down. Okay, and all I do is initially reset, and then just wait for a certain amount of time, and that's just going to keep, because once I'm out of reset, it's just going to keep counting up all the time. Okay, so what does it look like? Here it is. Okay, if you want to see it, this is a net list, if you like, the gate level net list. You can see the 4 flops there, and then just do a reset. And then that's, if you run simulation, what you'll see here is that going across the top is the clock. Okay, and once it's out of reset, what you can see here is it just counting up. On every clock edge, it counts up and eventually rolls over, because there's only 4 flip-flops. So it's eventually going to get up to 15 and then roll back to 0. Okay, but then, so hopefully that's a very, very simple example, and I've deliberately kept it simple so I can just explain some concepts. So first of all, as a verification engineer, I look at what's my input space here, and my input space is a simple reset and clock. Okay, my state space is 4 bits. That's going to give me 16 combinations, and also I've got 4 bits on my output, so I've got 16 combinations on my output. Okay, so my question to myself there is, what's my minimum verification plan? What's the minimum I need to do to make sure this works? Okay. Also, I forgot there's just a reset there as well. You can see if you look closely, you can see a little reset right at the beginning. Okay, and then rollovers at the end. Okay, so as a verification engineer, you may be asking yourself, well, what do I need to do? Do I need to do a reset in every state? Okay, so do I do a reset when my counter's at 1? Do I do a reset when my counter's at 2? Do I do a reset when my counter's at 3? Okay, and these are valid questions to ask with a verification engineer. Okay, but this is a very simple design. Okay, there's only a few states, so this may be manageable for 16 states, but typically your design will have billions and billions of states. Most chips have more states than there are stars in the universe. So it's not scalable. This type of thing is not scalable. And you also go back to that question, doing a reset in state 5, does that give, and then state 8, am I adding any confidence to my chip by trying to do resets in all of those states? And typically your answer to that will be no. It doesn't add to my confidence. And so you're always saying to yourself, is this scalable? Is it going to improve my confidence? Do I vary the clock speed? If you're doing a digital design, typically you don't really care what the clock speed is, because you're just doing simulation. Okay, all you're doing is simulation, and whether that's running twice as fast or half as fast, you don't really care, because all it's doing is counting up. So quite often you don't really care about the clock speed either. As a functional verification engineer, if you're doing there's some types of software verification where you would care, and that might be where you've got different clock domains in your chip, and one signal is passing from one clock domain to the other, and that's a known source of bugs. And you possibly do care about clock speed. Okay. So what we can do now is start to think about the way, I just want to talk about the way we think about a design as a verification engineer. I can think about my design as a state machine. This state machine is a simple one. It only has 16 states. Okay. And the output logic here is decided completely by the next state. Okay. Um, so, and then the next, you've got some logic here to decide what the next state is going to be. Okay, so these flops here are retaining your state. So we got 4 flip-flops, they retain the state, and my next state is just here. The input is a clock, so every time there's a clock, I know to go to the next state to count up. Okay, so we can represent this as a state machine, and there's 2, a million or more. Okay. And you can represent that mathematically as well if you want. So, for example, the output function FO is either going to be based purely on state, or for a medium machine, it's going to be based on state and input. Okay, so we can represent it mathematically if we want. Okay, and then you can draw this. So I can draw this here. There's my 4-bit asynchronous on the left hand side, and all I'm doing is going round and round and round that circle. Okay, on the right hand side, what I've said is that the asynchronous counter is now modulo 14. So there's 2 states that are missing, and I'll put them as red. And also, because it's up and down rather than just up all the time, means I can go backwards. See, this state machine is already getting more complicated. Okay. And so, and this is a 4-bit. This is 4 bits. It's got 4 flip-flops. Inside, just think about CPU. Inside the CPU, you've got typically 32-bit CPU. If you've got an ARM or a RISC-V, it's becoming more popular now. That will typically have 32 registers in there. Okay, so you're already talking about 32 times 32 states, flip-flops inside just the registers inside your CPU, and 2 to the power 32 times 32 is a huge number. Okay, and this is why this explodes so quickly, and that's why a lot of this you're having to think about, how do I cut down this verification space as much as possible. And what I'm trying to do here, and I've alluded to some of these numbers here, is that you can't hit all the states, and you can't do everything in all the states. So you try to pick out what are the interesting states. Okay, so we're always just, and I've skipped a lot of this. Hopefully, I've explained it, and again, you can read it in the PDF. You're always, after a verification engineer, trying to work out what are the interesting states, what are the most interesting states for me as a verification engineer. Okay. And I try to represent this here. So obviously I can't draw 2 to the power 32 times 32. So I've put a few dots there. They're all the potential states. Okay. And then if when I run a simulation, okay, what I'm doing effectively as I run through time is that I'm going through different states. Some of them are going to be illegal, as indicated on that previous state machine. So now my simulation wants to avoid the illegals, and now I can identify the interesting. Okay, and so what I'm trying to do is just pick out of all those states, out of those billions and billions and billions and billions of states, what are my interesting ones. Okay, if you've ever thought about simulation, and what I've shown there is simulation, and that's if you know about search algorithms, one is depth and one is breadth. Okay, simulation is very depth first. If you're ever interested to do breadth first, there's a way we sweep across rather than down first. There's a technique called formal verification, and if you like mathematics, yeah, then that's the place for you. And there's even bigger shortage of formal verification engineers as there are verification engineers. So that's a good place to be. And hello, he seemed to have lost. I'm not quite sure why we've lost the network. Okay,
Maybe.
and I've indicated that there. So I'm talking about simulation, which is what I call dynamic, because you're actually running code, whereas formal verification is static because you're just analyzing code. You're not actually running it, and that's where formal sits. And so this is the depth first, and that's the breadth first. Okay. And so what do our test benches look like? They start. We drive stimulus into the design under verification, and then we got a checker. Okay. And the drivers are typically here. I'll skip through some of these. We effectively you're best to treat the design as a black box. You don't look inside, and as soon as you start looking inside, quite often you get too much detail. What we do as verification engineers is a technique called grey box, where we try to monitor what's going on inside rather than actually use the actual internals. And this is what a UVM test bench looks like. And I know somebody hinted at before what a UVM test bench. We break our designs up into something which is doing stimulus generation, something which is driving signals into the DUV, something that's responding to the DUV design under verification. All these monitors to look at what's going on inside, and then we automatically check whether the design did the right thing. And we collect things called coverage. So when I said identify the interesting states, you do that via coverage models, and then you look to see how much of your coverage model you've actually covered. And then there's quickly on design hierarchy. I mentioned before that you get some IP from a company like ARM. You may get some IP from a company who's done a PCI interface. And so quite often you've got very hierarchical designs that start with a unit. That's an ALU, very simple ALU that works its way into a CPU, and the CPU works its way into a chip. So we get this hierarchy all the time, and we split our verification into that hierarchy as well. And we start the unit level verification. Then we move on to the subsystem verification. And then we move on to the top level verification, the chip level verification, if you like. Okay. And as you go through here, you should be finding most of your bugs down at unit level. So that by the time you get to the top, you've got less bugs to find. That's what we try to do as verification engineers. Okay, so hopefully that was useful. We do have a lot of this training online, and that will be in the PPT afterwards. But I'll try and skip the marketing here. But hopefully that was a rapid introduction to a very, very big subject. And I'm just aware of the time because I should be, I think, handing over to Peter now. Okay. But so I'll stop there. I'm around during the break if you want to ask me a bit more about digital verification. But I'll stop there, and I'll just quickly nip to Teams, which may be the thing which lost this connection before. Where's Teams gone? Okay, because I'll just upload your. In the chat, there should be your presentation in the chat. Quite sure it's gone. It was there. Sorry? Okay. This one? This one. Perfect. Thank you very much. Okay.